Can the camera see them?
We might have to check that. I feel like the screen would be easier, right? I just write it on the... Yeah. Okay. All right. So those of you that are joining us on the stream, hello. I'm here with Kyle. Kyle will be taking through the first two topics. Hope everyone's pumped. Thank you for everyone who's joining live. We'll get started.
Okay. Hi everyone, my name is Kyle. I'll be taking the first two chapters today, and Brendan will be taking the next three, I believe.
Well, yeah, we'll have another section tomorrow.
Yeah.
Section 3 and 4.
Yeah, cool.
Just for section 3.
Oh, okay, cool. Awesome. Okay. So yeah, I guess today I'm taking chapters 1 and 2, and Brendan will be taking chapter 3, and tomorrow we'll go through the rest with Brendan and Matthew. So yeah, I guess we can just get started then. So yeah, today we'll be going through the first two chapters, Introduction to Codes and Ciphers, and Error Detection and Correction. Let's see, should we fill out the attendance form first? So yeah, if everyone here can fill out the attendance form, that'd be great. I'll leave this up for a minute while we scan the QR codes. Cool. Do we need to do this?
If you're watching the recording.
Oh, okay, cool. Okay. I guess there are more QR codes, but okay. Cool. Okay. So on to chapter 1, Introduction to Codes and Cipher. So I guess for this chapter, it's all about thinking about how we can encode and decode messages, knowing that our messages might be, I guess, messed up midway during transmission. So we have some potential noise. So let's just say if you're trying to transmit a message, say message here equals 1001 from the sender to the receiver. So during transmission, noise might occur, which kind of messes up our transmission. So if you're trying to send 1001, the receiver might get 1011. And the first chapter is all about how we can rectify these mistakes and make sure that our receiver receives the message that we were trying to send. So let's move on to some definitions first. So we first have the source alphabet defined as the set S with the probabilities P1, P2, all the way up to PQ. So what we can think about the source alphabet is, the source alphabet defines the information we're trying to send. So let's supposedly say we have a scenario where I'm trying to talk to, I guess me, I'm trying to talk to Bob, and I'm trying to say hello. So in this case, the source alphabet will be just the English alphabet, because the message I'm trying to send composes of the 26 letters of the alphabet. And they also have a probability as well, because as you might imagine, if I'm talking to Bob, I'm not going to use the letter Z as much as I'm going to use the letter E. So probabilities will come in more use when I think Brendan, not today, but tomorrow when we go through compression algorithms. Maybe that is today. But yeah, that is just something to be aware of for now. And we also have the definition of the coded alphabet, which is the set C. And the coded alphabet kind of basically represents how we're going to transmit our source alphabet. So supposedly we have the source alphabet ABC, as you can see on the screen, and we have the coded alphabet of 0 and 1. Something we can do is we can encode the source alphabet by encoding A to 0, B to 10, and C to 11. So in this case, the message we're trying to send, ABBC, which is composed of the source alphabet, will first be encoded into 0101011, the code alphabet, and that's the message we're going to send to the receiver. So that's just some basic definitions out of the way. And cool. And some basic intro to modular arithmetic. I'm sure everyone here kind of knows, hopefully knows some basics about modular arithmetic by now. But just as a reminder, in this course, for the first two chapters at least, we're going to be working mostly in Z2, which is basically the set of integers modulo 2. So this set contains the numbers 0 and 1, as you may know. And that's primarily the set we're going to be working with for the first 2 chapters. Some other things to be aware of is we have some rules about modular arithmetic, which basically says if A is congruent to, how does this, if A is congruent to B mod n, and if C is congruent to D mod n, basically we have some properties about addition, subtraction, multiplication which holds. So for example, we have like A plus C is congruent to B plus D mod n. And similarly, you can imagine we have A minus C congruent to B minus D mod n, and so on and so on. Cool. So that's just some basic introduction to modular arithmetic. Again, some basic introduction to probability. So some things you might need to know for the first 2 chapters are, firstly, the binomial distribution, which basically tries to model a distribution of a random variable x, which can either result in 2 events. So it can either result in E or the complement of E with probabilities P and 1 minus P. And it has the probability mass function, which is given by this formula here. And essentially, this is the classic way to model, for example, how many ways are there of, let's say I'm flipping a coin. So supposedly if I flip a coin, or I flip n coins, I guess like number of ways to get k heads, and that'll be given by n choose k, p in this case is half, if you assume it's an unbiased coin, to the power of k times half to the power of n minus k. So this basically counts the number of ways. Well, if you have n events, we have k successes and n minus k failures. And it gives the probability of that. And that's kind of how we get the PMF here. And again, we have Bayes' rule, which basically aims to give us a way of calculating P of x and y. I'm just going to write it shorthand like this. In terms of conditional probability. So we are given that P of x and y is equal to P of y given x times P of x over P of y. And this bottom summation here basically sums to P of y. But this is another version of Bayes' rule, which you might be more familiar with. So yeah, that's just, I guess, probability prereqs out of the way. And we'll go into this further in depth when we actually deal with the questions. So don't worry too much about them for now. Cool, okay. So, onto the first code, which we will have seen in this course, and it's a 7-bit ASCII code. And the 7-bit ASCII code, basically, I guess like why it was created was it's a way to encode characters in binary, right? So basically, if you're trying to send characters like A to Z, capital A to Z, I guess like hashtags, exclamation marks, like @ signs, basically, in the old days, your computer encoded them in the ASCII format. And since there are basically around 120-ish characters, that's why with 7-bit, we can represent 128 characters, and that's why it was enough to represent all the sendable characters in the universe back in the days, before basically all the other languages got added. And it basically, for 7-bit ASCII, we're basically just encoding a letter, let's say A, in its ASCII representation, which might be something like 10011010. I have no idea what A encodes to, but that's just an example. Cool. And now we have the extended ASCII code. So the extended ASCII code is just like the 7-bit ASCII, but we have an extra bit in front now, which acts as a check bit. So for the 7-bit ASCII, as you may know, A here is represented by 0110010 in ASCII. And
1 second, just fix the camera.
oh yeah,
Sorry for the interruption. The camera just frozen something. Let's make a new one. What do you mean, sir? So, that's let's just refresh. Should be good now. I can just try that from this variable.
Alright, cool. Thanks for that. So basically, I guess the extended ASCII code is just 7-bit ASCII, but we add a check bit in front. So this gives us more redundancy, because instead of just conveying 7 bits of information, we now have 8 bits of information, and 1 bit is what we call the check bit. So essentially, if A was represented by 011, 0010, we now add a bit in front, which turns the total number of ones in this ASCII representation into an even number amount of ones. So before we had 3 ones, which is why we add a check bit of 1 in front to make it 4 ones, resulting in an even number of ones. So A gets turned into 10110010. And now by using up this extra bit to convey, I guess, redundant information, we now have a way to determine if the code was corrupted during transmission. And we can see that in a second. So yeah, another definition, burst noise is a form of noise which causes errors in consecutive bits. And essentially, if you can imagine, if A got changed, let's say this bit got flipped in transmission into a 1, which will turn it into 10111010. If the receiver now receives this code, they will know that it is incorrect now. Why? Because we have an odd number of ones. Imagine before we didn't have the check bit, so if this 1 wasn't here, and that bit got flipped, we had no idea of knowing whether that was just, the sender trying to send the letter, I don't know, like H, or if the sender was trying to send A, but it got corrupted during transmission. So with the extra 1 bit of redundancy, that basically tells us whether we can detect up to 1 errors essentially. So cool. Moving on. Another basically very similar code is the 8-bit ASCII burst code. And essentially the 8-bit ASCII burst code is just the same as the extended ASCII, which is an 8-bit ASCII, which is the normal ASCII with a checksum bit in front. But for the 8-bit ASCII burst code, we also have what's called a ETB at the bottom, which I believe stands for an transmission block. And essentially, the use of this extra row at the bottom is again for extra redundancy. Because as you can imagine, we have our 7-bit ASCIIs here in this top right square of the matrix-like shape. We have the 3 bits, we have the 3 bits which provide redundancy, just like the extended ASCII, but we now have this final row, the ETB, which aims to provide extra check bits as well. And how the ETB works is basically now every single column has to sum to an even number of ones. So in this setup, we have every column and every row all have an even number of ones. Like that. And basically, this aims to prevent burst noises from, I guess, disrupting our transmission. Because as you can imagine before, if you had an 8-bit ASCII, like 10100011, is that 8? That's 7. 1 more 0. Cool. And basically, this is a valid 8-bit ASCII, right? We have 4 ones, which is the even number of ones. Imagine during transmission, 2 bits got flipped. Let's say these 2. In this case, the resulting message will be 10111110. And if the sender sends the message, which is above, and the receiver receives the message, which is below, the receiver thinks the message is still correct, because there are still an even number of ones, and for the 8-bit ASCII, there's no way of detecting an even number of errors. However, with the 8-bit ASCII burst code, in this case, if 2 bits got flipped, let's say these 2, we can now detect an error. And the reason why we can detect an error is because if both of these bits are now 1, let me switch colors, 1 and 1, we can look at the sum of these 2 columns. These 2 columns now have an odd number of ones. So we can determine this column has been mangled somewhere during transmission. This column has been corrupted somewhere during transmission. And knowing that these two columns have been corrupted during transmission means now we can detect more than a single error. So we still can't know exactly where the two errors occurred, because they might have occurred in this row, or this row. We can't be sure of which row occurred in. But at least now we know our message got, I guess, disrupted somewhere during transmission. So yeah, does that all make sense? Cool, okay. Nice. Moving on now. We now have a different, I guess, code now. We have ISBN numbers. And as you may know, ISBN numbers are used to uniquely denote books. And they kind of share the same concept as what we just came up with the 7-bit ASCII. But they kind of add this extra position argument as well, which can be, which you can see here from the I. The I basically denotes the position of the number in the checksum. Well, sorry, in the ISBN number. So, and basically we require this summation to sum to 0 mod 11. Basically, the reason why they put this, I guess, position argument in the checksum, well, sorry, in the ISBN number calculation is ISBNs are good in two ways, because ISBNs can, one, detect one error, but due to the way that they put this I argument in the summation, it can also detect two swapped numbers. So as you can imagine, if there's no positional argument I in the summation, if let's say the summation just required the sum of xi to be congruent to 0 mod 11, then if I flip two digits, then that's still a valid ISBN number. But now, if I specify the checksum is given by I times xi, if I flip two numbers, the checksum will be different, right? And basically, that's essentially why ISBN has this special feature. And again, for example, we can try out the example here. It says 0387978127 is a valid ISBN. And how you verify that is simply by summing everything up. So we have, I'm not going to do the whole thing, but you'll just do 1 times 0 plus 2 times 3 plus 3 times 8 plus 4 times 7 and so on. And in the end, you should get a number which is congruent to 0 mod 11. And that's how you know we have a valid ISBN. And similarly, if you sum this number up using the function above, you'll find that it is not congruent to 0 mod 11, which means it's not a valid ISBN. Cool. So moving on. So ISBN 10 code can detect errors including a wrong digit or the interchanging of two digits. It cannot correct an error, so even though we have a wrong digit, there's no way to correct this error, because it can occur in any of the 10 digits, and we cannot detect which digit it occurred in. So yeah, basically same thing as the extended ASCII, we can detect one error, but for ISBN 10 code, we can also detect the interchange of two digits, whereas the extended ASCII cannot. So now we have a final exam question, question 1A, and it says, check whether the sequence 09091170064 is a valid ISBN. So same thing as before, how we do this is just sum everything up, right? We have 1 times 0, plus 2 times 9, plus 3 times 0, plus 4 times 9. I'm sure you guys get the gist now. So hopefully the next slide should contain the summation. Yes, it does. And as you can see, it sums to 208. And we can verify that 208 is not divisible by 11, which means it's not congruent to 0 mod 11, which means it's not a valid ISBN. And that's how we can verify if something's a valid ISBN or not. And again now, consider how we can make this valid. There are a number of ways to make this valid. We're not too sure where it happened, so maybe we can just try to see if we can change the last digit to make it valid. So how we might do this is, well, let's just try sum everything up except for the last digit. So if we sum everything up except for the last digit, we should get basically 168. The reason is why, if you sum everything up, including the last digits, we get 208. So if you remove the last digit, we should get 168. So we know the sum of the first 9 digits sum to 168. So let me just write this out. So if you sum everything up, that should equal to 208, and that should equal to 168 plus 10 times the last digit, or 10 times x10 for the 10th digit. So that's kind of what we have, right? But now we know x10 is flipped. So assume that we know x10 is flipped, we're going to find what value x10 should take on. So we know that 168 plus 10x10 should now be congruent to 0 mod 11. That's kind of what we know. And again, there are many ways you can now solve this equation. One way you have, which works every single time, is you can simply say, well, maybe firstly, we should try to simplify 168. So we can take 168 mod 11, and you should get 3, I think. Correct me if I'm wrong. 3 plus 10x10, which is congruent to 0 mod 11. I think that's correct, but I'm not too sure. Oh wait, yeah, I think that's correct. So now we can, then, one way to solve this is you can write this as 10x10 is congruent to minus 3 mod 11. And then what we can do is you can find the inverse of 10 mod 11. So the inverse of 10 mod 11 basically is a number where 10 times that inverse, let the inverse of 10 be y. You have 10 times y equals 1 mod 11. And here we call y the inverse of 10. Oh, damn. Inverse of 10. So imagine you find y, taking times y on both sides, and then you will just get x10 is congruent to minus 3y mod 11, and you can simply solve for x10. So that's one way of doing it, but that requires using the extended Euclidean algorithm to find the inverse of 10, or you might just guess it, I guess. Another way to solve it, which I think is easier, is 10 is the same thing as minus 1 mod 11, right? So you can simply say 10 times x10 is the same as minus 1 times x10 is congruent to minus 3 mod 11. And here we can just find that x10 should be 3. And if you check the answer, that is also correct. So yeah, that's just one way of solving mod equations sometimes, which you can use, which will help you speed up your work significantly. Another way to do it is you can just sub in 0 to 10 for x10 and just figure out what x10 should be. So yeah, does everyone kind of follow the working? Cool, okay. I'm going to assume that's okay. And then we know that this is now a valid ISBN when we change the final digit to a 3. Cool. And yeah, that's the first chapter. So congrats on getting through the first chapter. Only 6 more to go. Chapter 2, we have error detection and correction. So now we're going to basically, I guess, make the idea more concrete of what it means to have noise in our transmission channel. So basically, I think this is called a binary symmetric channel. And essentially what it means is just the sender sends a bit and the receiver receives a bit. But then there's a probability P, the bit gets messed up. So 0 can get messed up into 1 and 1 can get messed up into 0. And they have the same probability. So the probability we send a 0 and they receive a 1 is equal to P, which is the same thing as the probability we send a 1 and they receive a 0. And again, if the bit does not get messed up, then if you send a 0, they will receive a 0. If you send a 1, they'll receive a 1. And basically, the focus of this chapter is how can we deal with this noise in our transmission channel? Because this will occur in real life. So this, I guess, chapter is just about how we can have some encoding schemes which will help us to detect these errors. So cool. And yeah, the 8-bit ASCII burst code and the ISBN 10 code also helped us basically detect up to 1 error. And now we'll try to basically formalize this idea and generalize this to more than 1 errors. So we have the first code, which is a binary repetition code, which might be what most of us think of when we are asked to come up with a I guess, like error detection code. And essentially how this code works is if you want to send let's say, a single bit from the sender to receiver. So if I want to send 1 from the sender to receiver, how I can encode this is just by, like, if you tell me that 1 bit's going to get flipped, then what I can do is I can just send 3 bits, right? I can just send 1, 1, 1 instead of sending a single 1. And if I know only a single bit is going to be flipped, then if a single bit is flipped, I can still recover the original message, right? Because if there are more 1s and 0s, then we can just kind of basically tell that the original message was 111, even though if the receiver receives like 110, we can then correct this to a 111. And that's the simplest form of, I guess, error correction code. So yeah, so a binary repetition code is simply a code that repeats a particular symbol a fixed number of times. And they can be even length or odd length. And this will have some impact later on, as you can see, whether we choose even or odd. So we have 3 strategies. We can either, in this case, correct up to 1 error, 2 errors, or no correction. And basically, depending on which strategy we choose, this will also influence how many errors we can detect. And that's kind of the weird thing. So depending on which strategy we choose, this will influence the number of errors we can detect. And the simplest way of like reasoning about why which strategy we choose will influence the number of errors we can detect, is let's just assume that, you know, we're dealing with this code here. We have a 5-digit binary repetition code. If you try to send 0, we'll be sending 0, 0, 0, 0, 0 instead. Let's say assume we use strategy 1, right? If you use strategy 1, that basically means if you receive something like 0, 1, 0, 0, 0, we'll correct that to 0, 0, 0, 0, 0. And, well, okay. And essentially, anything else, let's say we receive 0, we receive 2 1s. So if you receive 1, 1, 0, 0, 0, we're not going to correct this. We're going to instead simply say, error detected. Cool. And then similarly, for 1, 1, 1, 0, 0, we're going to say error detected as well. I'm running out of space, so let me try to rub some stuff out. Okay, there we go. And if you receive 4 1s, 1, 1, 1, 1, 0, the thing is, in this case, now will be messed up. Because if we're trying to send 0, and the channel basically flipped 4 of the 0s to 1s, then in this case, if you receive 1, 1, 1, 1, 0 on the other side, if you use strategy 1, we will then instead correct this to 1, 1, 1, 1, 1. Because we think that we were trying to send a 1 actually. So even though we're trying to send a 0, if 4 of the bits gets flipped, then we will correct the message to 1, 1, 1, 1. And I guess this will result in like an incorrect decision in the end. So essentially, if you choose strategy 1, if you correct 1 error, we'll basically be able to detect up to 3 errors, right? Because imagine if you correct 1 error, we can detect 1 error here, 2 errors here, and 3 errors here. But if you have 4 errors here, then we cannot detect that. So if you choose strategy 1, we can detect 3 errors. And we're going to do one more example. If you choose strategy 2, if we instead say 2 bits flipped equals we correct as well, then that means if you have 3 bits flipped, what will happen is we can't detect this anymore. If you have 3 bits flipped, we'll instead correct this to 111, 11, and this again will be another incorrect decision, which means now we can't detect up to 3 errors. We can also only detect 2 errors. So as you can see, if we increase the number of errors we choose to correct, we will correspondingly decrease the numbers we can detect. And actually they go up, I guess, like by the same magnitude. So if I detect 2 more errors, I will then be able to correct 2 less errors. If I want to correct 1 more error, I'll have to detect 1 less error. And strategy 3, if we do not correct anything, we can detect 4 errors. Because the only case we cannot detect is when all 5 bits gets flipped. And yeah, essentially this is how it kind of works. And this also gives, I guess, an intuitive explanation to why we have the formula E plus F equals D minus 1. If you remember this formula, it's in your course notes, so no need to memorize it. But essentially, this looks like ETF, but this is meant to be a plus sign. Let me drop this out. E plus F equals D minus 1. So I think E was defined in this case as the number of errors we can correct, and F is defined in this case as the number of errors we can correct, or the other way around. Well, essentially, as you can see, if we increase one, we'll decrease the other. And the reason why is basically because of this argument we just showed here. So yeah, does that all make sense? Cool, awesome. So yeah, gonna move on now. For 2t plus 1 or 2t plus 2 fixed length code, we can correct up to t errors. And the reason, the way you can prove this is by using the formula above, which said, again, E plus F equals D minus 1. In this case, D will be either 2t plus 1 or 2t plus 2. And basically, by this formula, basically it will tell you that we can correct up to t errors. And this kind of makes sense intuitively as well, because if you imagine what 2t plus 1 and 2t plus 2 is saying is basically, if I have the code, let's say 0, 0, 0, 0, 0 here, for let's say t equals 2, because when t equals 2, our 2t plus 1 code has length 5. And if you have the code 1, 1, 1, 1, 1 here, this is also for t equals 2, right? So we have one code on this side and one code on this side. And basically, if you kind of plot this on a number line, what do we plot? We kind of plot the Hamming distance of codes. So what that kind of means is this code here will be like 0, 1, 0, 0, 0, 1 bit flipped. This will be 2 bits flipped. This will be 3 bits flipped. This will be 4 bits flipped. And this will be 5 bits flipped. Basically, we can only correct errors that's within our half of the circle. So I'm sure you guys have seen this diagram before somewhere in the course. Well, like when you have taken the course. But essentially, they kind of make 2 circles. And what the 2 circles kind of mean is any code that lies within this circle, that is centered at 0, 0, 0, 0, 0, we can correct all the codes to 0, 0, 0, 0, 0. Why? Because basically, well, it doesn't really make sense to correct any code here to 0, 0, 0, 0, 0, because it's closer to 1, 1, 1, 1, 1. So basically, that's essentially why if these 2 codes are either 2t plus 1 distance apart or 2t plus 2 distance apart, we can correct all the errors within their radius, which is t in this case. So yeah, hopefully that kind of makes sense. So yeah, that's binary repetition code. And now we're going to be moving on to binary Hamming code. So binary Hamming code, same vein as binary repetition code, we are trying to detect up to a single error and correct a single error. And how binary Hamming code does this is by having this parity check matrix H. And essentially, how we can confirm if something is a valid code word, it's just we do H multiplied by X, and if this gives us 0, then we know it's a valid code word. So in this case, we have H times X equals, this is what we call the syndrome. And essentially, if H times X transpose equals 0, then we know that it's a valid code word. If it's non-zero, then we know at least 1 bit got corrupted. And that's essentially the whole gist of binary Hamming code. And we say it's an NK code. The reason why we say it's an NK code is because we say that the code has length n. So there are n bits in the code. K of the bits are info bits. So bits that we can change to send a message. And the other complement of the k bits, the n minus k bits, must be what we call the check bits. So these are the bits that are basically determined based on the info bits. So if you choose the info bits, I don't know, 1010, it will basically give us some check bits, which you must choose to make it so that H times X transpose, the syndrome, will be 0. Cool, awesome. So that's binary having code. Cool, okay, so we have example here of a common example is having 7-4 code, which means in this case, n equals 7. So we have 7 bits that we're trying to, well, our code is length 7, k is 4. And k equals 4 means we have 4 information bits, which means we now have 7 minus 4, which is equals 3 check bits. And the question says, why 7-4 and why not 6-4? In this case, this is 7. If we have 6-4, so if n equals 6 and k equals 4, then we will only have 6 minus 4 equals 2 check bits. And basically the short answer is 2 check bits just isn't enough. I think that's what the answer says. Yes, so however, since it does not have 3 check bits, it cannot be single error correcting or have a parity check matrix. The long answer is, if you're wondering why 2 check bits doesn't really work out, it's because, I'm not too sure if you remember, but there was basically a theorem that says, well, I basically said it a few times now, but I said like E plus F equals D minus 1. And in this case, you might be wondering, what is D? Well, D is defined to be the shortest distance between 2 possible valid code words. So D is the shortest distance. So in the examples before, for the binary, what was it called? Binary repetition code. If a binary repetition code was length 5, then 2 valid codes are 0, 0, 0, 0, 0 and 1, 1, 1, 1, 1. And their distance is 5, right? So that's what D meant previously. In this case, it kind of means the same thing. D is the shortest distance between 2 code words, well, 2 valid code words. So in our case, basically, why 6-4 doesn't work is because if you only have 2 check bits, as you can imagine, like one way of having 6 elements in this, I guess, like matrix is if H is size 6-4, then H will have 2 rows and 6 columns. And for 2 rows and 6 columns, let's just think about what we can have, right? We can have like 1, 0, 0, 1, 1, 1, and then we must have some like duplicates now, right? We can here have like, I don't know, like 1, 0 again, or like even 0, 0, or 0, 1. And basically, this makes it kind of bad. And the reason why it's bad is because you might remember that D of, I don't know, this code here, C, the code basically which is represented by this check bit, this parity check matrix H, is defined to be the minimum number of linearly dependent columns. I don't know why I put this annotation here, but D of C is defined to be the minimum number of linearly dependent columns. And if we have some double ops, so let's say, oops, this column and this column, they're double ops, right? If you have double ops, then that basically makes it so that D of C will be less than 2. And having this 0, 0 column here makes it so that D of C actually equals 1 in this case. And if D of C equals 1, then basically we get no error correction. Because E plus F, if E plus F equals 1, then basically we can only detect errors, we can't correct any errors. So the long answer why 6-4 doesn't work is because 6-4 only gives us 2 check bits, which isn't enough in this case. So yeah, hopefully that kind of makes sense. Yeah. Oh yeah, sorry. So I think E plus F equals D minus 1. E is the number of errors we can correct. Number of errors we can correct. Sorry, I'm not very used to writing with the stylus. And F is the number of errors we can detect. Cool. And then we must know that F is bigger than E. I might have swapped E and F around, but basically, the reason why F is bigger than E is because if we can correct 3 errors, then we can also detect 3 errors, right? So yeah, so in this case, if we have 2 linearly independent columns, like these two, then D equals 2, right? Which means E plus F can be at most 2 minus 1. So E plus F can be at most 1. And in this case, if we also know that F is bigger than E, then we basically must have E 0 and F is 1. which means we can only correct one error. Sorry, we can only detect one error. We can't correct anything. Does it make sense? Cool, awesome. And that's also why, basically, I think one common example of how we construct a Hamming code matrix for age is basically we just list all the numbers from 1 to something in binary. So let's say to construct a binary 7-4 matrix, what we would do is we just list all the numbers like 1, 2, 3, 4, 5, 6, 7 in binary. And basically list all the numbers from 1 to 7 in binary. This will make it so that no two columns are linearly dependent, which means D of this code equals 3, which means we can have E equals 1 and F equals 1, which means we can detect and correct exactly one error. So that's kind of why we construct the matrix this way. Cool. And some properties of the Hamming code is we set the dependent columns to the infill bits, the independent columns to the check bits. The reason why we do this is essentially because for the independent bits, we can set them to anything we want. Well, the independent bits, they kind of depend on the values we put for the dependent columns. So basically, for the dependent columns, we make it the information we're trying to send. And basically, that will give us some unique value for the independent columns, which will be the check bits. Cool. So we can see an example of that in a second. But firstly, I think this is just saying how we can detect errors. But I think this will be... Yeah, we can see that here, basically. So let's say we are using the binary 7-4 Hamming code, which we discussed before. The parity check matrix is just, we can write all the numbers in their binary representation from 1 to 7. 4, 5, 6, 7. And let's say we receive the message 1011101. 1011101. So now, if on a correct encoded message, we'll determine if the message was indeed correct or incorrect. What we can do is we can simply find the syndrome. And to find the syndrome, we kind of do matrix multiplication here. And we will get... okay, this is going to be a bit annoying. What do we get? Well, okay, I'll just try to do this. So we first get, let's see. Let me write this out. We get 1, 0, 1, 0, 1, 0, 1 plus 0, 0, 1, 0, 0, 0, 1 plus, okay, last one, 0, 0, 0, 1, 1, 0, 1. Cool. And since we're working in mod 2 arithmetic, if we just plus everything out, we'll get 1, 0, 0, 1, 0, 0, 1. Wait. Okay, I completely messed everything up. Sorry. I multiplied the wrong way. Okay, let's try this again. Okay. Cool, okay. So you're meant to multiply, I don't know what I was doing, but you're meant to multiply 1 with the first column and so on. So I guess that's an example of what not to do. So cool, let's just try to do this properly now. So
you just wrote the message about the alien so it's easy to see like with.
Oh, that's a good shout. Okay. So you have 1, 0, 1, 1, 1, 0, 1. Cool, okay. That is actually, yeah, very clean way of doing it. So we have 1 times the first column, 0 times the second column, 1 times the third column. I'm going to write this out in case I make a mistake again. 1 times the fourth column, 1 times the fifth column, and 1 times the last column, which is 1, 1, 1. Damn it. Okay. 1, 1, 1. And if you add everything up, we'll now get 0, 0, 1. Okay, cool. We finally got it correct. And we can see now the syndrome is not 0, right? Which means something happened during transmission and some bits got flipped. And now we can see which bit got flipped. And it must be the fourth column that got flipped. Why? Because basically we have 1 extra of the fourth column. And the way you can kind of think to yourself, like, why this means the fourth column was incorrect, is because basically, if you change the fourth column if you flip the fourth column, which is this one, a 1 to a 0, basically we're going to be getting rid of this sum here. So we will no longer have the 001 term in our sum, which means the resulting sum, the new resulting sum must be 000, which gives a zero syndrome, which means now it's correct. So basically, how we detect an error is just we work out the syndrome. If it's non-zero, we know something messed up. And how do we know which one got messed up? We just look at our parity check matrix, find the column which corresponds to the syndrome we got, and that must be the column that got messed up. So yeah, so in this case, the message should be 1010. This bit got flipped, 101. So hopefully that all makes sense. Cool. And yeah, thank you for that. That's a great way of calculating the syndrome by writing it on top. Cool. As you can see, the solution is here. Basically doing the same thing, take out 001, which means that this corresponds to the fourth column. Hence, we can correct the fourth bit and get the correct information. Oh, and one last thing. How do we know the information is 1101? Well, as we said before, we choose the independent columns to be the check bits and the dependent ones to be the information bits. The independent columns in this case are this one, and this one. Why? Because they're the leading columns. And this is in reduced, this is just in row echelon form, I think. So these four are the info bits. So 3, 5, 6, 7 are the info bits. And if you look at our message, 3, 5, 6, 7 gives the final information, which should be 1101. Cool. So the bit that got flipped was actually just a check bit. Nice. Hopefully that will make sense. Cool. Okay, so one final question before we move on. So this question says, check whether a random string of 15 ones and zeros has a 1 in 16 chance of being a code word in the binary having 1511 code. So, how do we approach this? Well, for 1511 code, we're given some information already. We're given n equals 15, k equals 11, which means we must have 15 minus 11, which equals 4 check bits. So how I can reason about it is in this code, we have 2 to the 11 valid codes. Why 2 to the 11? Well, for 2 to the 11, we have 11 information bits, right? So basically the information bits, they can be anything we want them to be. So we have 2 to the 11, combinations of info bits. For the final 4 check bits, they are determined solely based on the info bits. So if we basically choose, well, we have 2 to the power of 11 ways of choosing the info bits. If you choose them, well, if you set the info bits like set in stone, then the 4 check bits must follow. So we can't basically alter the check bits based on the info bits. They're basically already given to us. So essentially, let's say we take any random code, right? We have 2 to 11 valid codes, and we have 2 to the 15 total codes. So we can simply do a division here, and we can get, should be 1 on 2 to the 4, which is 1 on 16. So basically, if you randomly pick a string of 1s and 0s, then there's going to be a 1 in 16 chance of us picking the correct code. And the reason why is because for every single valid code, the check bits are predetermined. There's only one valid combination. So basically, if you choose a random string of 15s, 1s, and 0s, then basically we're choosing 11 random information bits, and the chances we get the 4 check bits correct are 1 in 16. Because if we have 4 check bits, every single check bit can either be 0 or 1, and to get 4 check bits correct, we're basically guessing 4 correct combinations of 0s and 1s. So that's going to be a 1 in 16 chance. Cool. Does that make sense? Nice. And we can see that here. So again, we have 11 information bits, but we do care about the values of the 4 check bits. And to guess all of the 4 check bits correct, we have to guess 4 times, and 4 correct guesses means a 1 in 16 chance. Cool. Final thing is we have this table here, which kind of represents the information rate. So I think R here represents the information rate, and the info rate is just the number of info bits over total bits. And what we'll see is with the binary repetition code, whoa, it's raining. with the binary repetition code, this R thing will approach 1. So basically, it means that the number of information the number of information we convey is equal. It's going to approach 1. And this is pretty good. But the thing is, this will only ever correct one error. And sorry, this is for binary Hamming code, not for binary repetition code. Binary repetition code kind of sucks because you have like one information bit and you have like, t total bits. So it's pretty garbage at transmitting information, but it is very good at correcting information. So yeah. Now onto some more definitions. We have Hamming distance and weights. So Hamming distance is simply how many bits between x and y that are different. And the minimum distance is just a minimum Hamming distance of every single possible combination of code words. So as an example, if you have code words 101 and 011, the Hamming distance here is 2, because 2 bits are different. And even if you're working in different, radixes, if you have like 120 for radix 3 and 102, the Hamming distance of this is still 2. Because only 2 of the columns are different to each other. So we don't really care about how much they are different to each other. We just care about if they are different to each other or not. So both of these examples, they have Hamming distance of 2. And Hamming weight is very similar, but instead, we're just comparing the number of ones in X to a string of zeros. So basically, the Hamming weight of, let's say, 1001 is just a Hamming distance of 1001 and 0000, which in this case is 2. And again, the minimum weight is just the minimum Hamming weight of all the code words in the set C, but we are not including the code word 0. So let's say we had a set C, which is equal to 000 and 101. Here, W of C will be 2, not 0. So hopefully that will make sense. Yeah. And to note D as a minimum distance, we will now develop an error correction strategy called minimum distance decoding. So we'll see what that means in a second. I think we've gone through this. That's what we came up with for the repetition code. And again, how to prove it, or how to reason to it, is just by using this formula, I think. Well, that's how I kind of do it myself. Cool. So I think we should move on to this question first, and then we can come back to what that part was saying. So basically, this question is saying that we're trying to send a code, and how we send the code is we kind of pack it into a cube. So we have a cube here, and basically they have, let's say we just have a 3x3 cube. And basically they have numbers written on each of the corresponding unit cubes. So we might have like 0 on this unit cube, 1, 0, and so on. So basically we are packing like a 1D message, or a 1D sequence of zeros and ones into a 3D cube. And essentially, what we do is we designate this smaller cube, that's n by n minus 1, by n minus 1, by n minus 1. So we designate this smaller cube to the actual part of the message that basically represents the message bits. And the other outer layer, so like these three, let me use a different color. These three, like this outer face on the outside of the cube is the check bits. So I don't think my diagram is too clear, but essentially I'm going to draw it again. Let's say n equals 3. So then we have a 2x2 cube, which contains all the messages. So this cube can contain 2 times 2 times 2, which equals 8 bits. And then we have this outer layer that contains all the check bits. I'm not very good at drawing, but hopefully you can kind of see what's going on. We have this outer layer that contains all the check bits. So essentially, we have n cubed bits in total. We have n minus 1 cubed info bits, which means we must have the difference, which is n cubed minus n minus 1 cubed check bits. And hopefully you can see what's kind of going on. This is just a generalization of the 8-bit burst code. So for the 8-bit burst code, we had a, I guess like this 7 by 7 kind of info bits here. And then we have like an outer layer which are these bits, and all of these bits here are the check bits. And here it's the same idea, but now we're generalizing this into 3D. And basically, what this is saying is, we require every single row, every single column, and every single, like, third dimension. I'm not too sure, like, what the term for it is. But we require all the sum to be 0 mod 2. So imagine you have a cube. If I pick any axes, let's say I pick the in and out axes, and I choose any single, like, one of the 9 valid squares for the in and out axes, the sum of that axis should all sum to 0. So that's just kind of what this sum is saying. It's saying that if we fix 2 of the coordinates and we vary the third dimension, then the sum should just sum up to 0. So essentially, every single column, if I stab through a column, that column sum should be 0. Every single row, if I stab through the row, that sum should be 0 as well. And every single one of the third axes, if I stab through it, that should sum to 0 as well. So you can imagine this is giving us lots of redundancy. And the question now is asking us, explain why the code C is 2 error correcting. And this should be, I guess, like, motivated by the fact that for the 7-bit, I guess, ASCII code, remember that was 1 error correcting. The reason why it was 1 error correcting is because if there's an error here, what happens is we can see the checksum for this column fails, because this will be invalid, right? If we are 1 bit flipped. And similarly, the checksum for this row fails. So for here, this will be invalid as well, because there will be an odd number of 1s. And if you have a column that fails and a row that fails, we can pinpoint exactly where it failed. And that's kind of what the 7-bit ASCII burst code kind of did for us. Well, it should be the 8-bit ASCII burst code. But yeah. And the thing is, it was only 1 error correcting. Because if you had 2 errors, let's say 1 error here and 1 error here, basically what would happen is this row would now be incorrect as well, and this column would now be incorrect. And if we're in this situation, we can't be certain which ones were incorrect, because either these 2 could be incorrect, or these 2 could be incorrect. Both of these combinations will lead to the same 2 rows and 2 columns being incorrect. And in this case, we are basically stuck. So that's why for the 8-bit ASCII extended ASCII burst code, it was 1 error detecting and correcting. So one error correcting. So now we're going to prove this 3D variant is 2 error correcting, which sounds fair as a generalization. And I guess how you can kind of reason to yourself why it's 2 error correcting is because imagine we have an invalid bit in the cube, right? So we have a cube here, and let's say one of the squares is invalid. Let's think about the 1 error case first. If this square is invalid, we can easily figure out which one's invalid. The reason why is because imagine you have this unit cube here, which contains the bit that's flipped. If I stab through it vertically, then that column should now have an invalid sum. So I know that column is now messed up. And if I stab through it horizontally, then that row should also have the incorrect sum of 1s. So just from 2 stabs, the column stab and the row stab, I now know that square is the incorrect one. So that's why it's 1 error correcting. So now we can think about why it's 2 error correcting. So let's say 2 of the unit cubes in my big cube is now incorrect. So I guess like the weak point about why this 2D case didn't work before is because if you had 2 errors that were incorrect, let's say here and here, it was impossible to tell where the 2 errors, where the 2 errors exactly are. But in the 3D case, we can tell where the 2 errors are. The reason how we can tell that is because imagine we just focus on a single error first, right? We just consider this error. Again, if you stab through it horizontally, we might stab through the other error as well. So imagine if the other error was here on the same horizontal plane as the first error. In this case, if you stab through it horizontally, we will see that the checksum actually succeeds, right? Because 2 bits flipped equals an even number of 1s still. Does that make sense? However, if let's say they lie in the same horizontal plane, then we know they cannot lie in the same vertical plane, right? So if you do this vertical stab, then we'll see that this vertical sum will now be incorrect. So even though the horizontal sum was correct, we can see the vertical sum is now incorrect. And then if you do the third dimension, if you try stabbing through it like into the page and out of the page, this will also be incorrect. So for every single cube, for every single square in the cube, we have like 3 axes where we can check its checksum, right? We have like the horizontal one, the vertical one, and the in and out one. The thing is, only one of the axes might be, I guess, like a bit confused by the fact that we now have 2 errors, right? So only one of the axes, in this case, the horizontal one, says it's correct, thinks it's correct, because there are 2 errors in the same horizontal plane. However, if there are 2 errors in the same horizontal plane, there can't be 2 errors in the same vertical plane or the same in and out plane. And with 2 axes, we can determine exactly where the error is located. So basically, that's why even with 2 errors, the 2 errors can only be like present in one of the planes together. Either in the horizontal one, they're the same, the vertical one, they're the same, or the in and out one, they're the same. So we can still use the 2 other planes to figure out where exactly the error occurred. So that's basically part A. Part B, very similar, but it says, state the maximum value of t for which C can always detect up to t errors. So now it's about error detection, not correction. So again, we can first consider a 2D case and try to work our way up. For the 2D case, when it will break is when basically for a column, we must have an even number of flips, right? Even number of noise. So if you have 2 flips in the same column, then this column will think it's correct, even though it's wrong. However, for this row, it will think that the row is correct, even though it's wrong. However, column-wise, these 2 columns will be incorrect, right? So how can we confuse the error detecting if you're thinking that these 2 columns are correct? It's also by having 2 more errors in both of these columns. So if we have like an error formation like this in a rectangle, then we know this column is meant to be wrong. But since we have 2 flips, it will be considered correct. Similarly, this column is meant to be wrong, but since we have 2 flips, it will be considered correct. Similarly for this row and this row as well. And that's how we can confuse like the 2D variant of the 8-bit extended ASCII. For the 3D variant, it's very similar, right? For 3D variant, imagine we had like an error here. Again, I don't think I can draw this very well, so I'm going to try my best to explain it. But if you had like an error here, then basically, each face, well, you can kind of think of it this way. If you have an error here, then if you consider the face, like this face here containing the error, this is exactly the same as a 2D variant if you consider a single face of the cube. And again, as we reasoned about in the 2D case, for this to be considered correct by the checksum, you must have it in a rectangle formation like this. And that kind of fixes it for a face. But we also have another different plane, right? We also have to make sure like for this plane here, is considered correct as well. And to basically do this, how you can construct it in the 3D space is just by having, it's just by having an error like here, 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 in a cube shape, and like there, and there. Okay, this is a very bad diagram, but essentially, okay, that's kind of horrendous. But imagine like for the 3D case, how you to basically have errors, which basically confuses the checksum feature of the 3D cube. What you need to do is basically have a rectangular prism, or have 8 errors situated on a rectangular prism in the corners of a rectangular prism. So if I have a rectangular prism, I need 8 errors here, like 1 error here, 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 1 error in this corner, 1 error in this corner, and 1 error in this corner. If you have 8 errors like this, basically any row will have 2 errors on the same row. Any column will again have 2 errors on the same column, and any vertical stabs will have 2 errors on the same vertical plane. So every single plane will have 2 errors going through it. So no matter which way you check the checksum, all the checksum bits will be correct. So hopefully that makes sense. So if you have 8 errors, then we can't detect 8 errors. So for B, we can only detect up to 7 errors. We can detect up to 7 errors. So yeah, hopefully that makes sense. Have any questions? Feel free to let me know. But if not, we can move on to sphere packing. So what is sphere packing? It's basically saying that if you want to have a T error correcting radix R code, we need this condition to be satisfied. And how you can reason about this is, for every single code word in C, so let's say this is like C1, like one code word here, the second one here, third one here. Basically, if you want to correct, I guess, T errors, essentially, you want each of these to have a sphere of radius T. I drew this kind of not to scale. But the reason why you want all of these to have a sphere of radius T is because you can imagine, like, the way we are looking at it is in terms of, I guess, their Hamming distance. So remember we defined Hamming distance as how many bits they are different before. And the reason why we have spheres of radius T is because anything within a Hamming distance of T, we can correct to itself. So for a T error correcting code, it simply means for any single message, right? If T bits are flipped, we're still going to correct the code to C1. So if C1 was something like 10001, and let's say T was 2, for any 2 bits flipped, we're going to correct everything to C1. So if C1 is something, so if the code like 10101 appeared, this will be corrected to C1, which means like 10101 is kind of close to C1, and it belongs in this sphere. So everything in the sphere gets corrected to C1. Similarly, everything in C3's sphere gets corrected to C3, and everything in C2's sphere gets corrected to C2. And what is in each of their spheres is just all the codes which are within a Hamming distance of T to it. So this is basically the case. And we do not want the circles to overlap. Because why? If they overlap, then we're basically going to correct 2 codes. Sorry. So if 2 circles overlap, it kind of represents the fact where this code here might get corrected to this one, or it might get corrected to this one. We have no way of knowing. It's within the Hamming distance of T to both C3 and C4 here, and we have no way of knowing which one we should correct it to. So basically, we do not want the spheres to overlap. And that basically gives us the intuition for this sphere packing condition, which basically just says the spheres can't overlap. How it says that is basically it says, for every single code C1, C2, C3, they should have enough, I guess, like redundancy around each of these spheres so that they will not have to overlap. And that's kind of all the condition is saying. So it's saying for every single code word in C, they must have a big enough sphere around it. So this summation term is just determining how many elements should be in this sphere. And it should be less than the total number of elements in the set of messages we can transmit. So it's basically saying that if each sphere has to be this large, then we want all these spheres to be non-overlapping. So all the volumes of the sphere has to be less than the total space of messages we have. And that's kind of what this condition is saying. Cool. And basically, I think in the lecture notes for this year, the condition is written out as C times the sum from I equals 0 to T of n choose I, less than R to the n. Sorry, less than, not R to the n, less than 2 to the n. I think this is what you'll see in the lecture notes. The reason why is we just substituted R equals 2 to this formula. So this is a more generalized formula, which I don't think you need for this year. I'm not too sure. Don't quote me on that. Sorry? Oh, we need a test? Okay. So I guess we will need this for this year then. Thank you for that. Cool. Hopefully that makes sense. I'm running a bit low on time, I think. How many more questions do I have?
45.
Sure, but I think Brandon's meant to take the other 45 minutes. So I'll try to speed this up a bit. Sorry?
We have the root of.
Oh, okay, awesome. Oh yeah, you mentioned that to me before. Cool. So now we have binary linear codes, which is just an extension of Hamming codes. And basically, binary linear codes just says the set of code is basically the null space of the matrix H. So we have X here is the null space of the matrix H, and it's a more generalized, I guess, like way of describing just the binary Hamming codes we saw before. Cool. We can just have a go at one of the questions. So suppose we have a binary linear code with the parity check matrix as given below. We receive the message 10001, correctly encoded message to determine what the information was. So we can use the same strat we used before. We write the message on top, and we try to sum this up. So we will have 1000 plus 1001, which is equal to 0001 in mod2 space. So we can see in this case, this doesn't equate to any of the columns seen before. So you might be wondering, what's going on here? Well, the first thing you can conclude with is that it is definitely incorrect, right? Why? Because the syndrome here is non-zero, which means it is I guess you can say it's a invalid code. Something got flipped along the way. So what got flipped in this case? Well, in this case, two things got flipped. That's why 0001 isn't found in any of the columns here. So 0001 is actually a linear combination of two columns in the matrix H. And it is a linear combination of the columns, what is it? Did I add something wrong? No, I don't think so. Okay, cool. So I guess it is a linear combination of this column, and this column. Does that kind of make sense? Cool. So we can basically now conclude that these three columns, or I guess, oh, sorry. It's a linear combination of this column and this column.
We had it.
Sorry?
That is all we had it together.
That is indeed the ones we added together. But I think, wait. Okay, yeah, I'm not tripping. So basically you can imagine that like these two are the check bits of the matrix, and the middle three are the information bits, right? So yeah, so in this case, the two check bits got flipped to the incorrect ones. And the three middle information bits are what we want to kind of preserve, right? So in this case, again, the two check bits on both ends got messed up. So in this case, they're indeed the ones we added, but since we want the syndrome to be 0, we still basically know that the first column and the last column were incorrectly added. So the actual message is just 00000, and we can see that here as well. So again, if we add this up, we'll get 0001 mod 2. And to get 0001 from the column, from the matrix H, it is just the sum of the first column and the last column. Which means we have errors in the first and last bits, which means the original message was 00000, and the information is 0. Cool. Does that make sense?
Could you also extend the middle three?
You could have, and I think basically that's why we have the strategy that we are basically correct 2 error, and we will detect 2 errors. So that's the strategy we chose, right? We could have also said we were gonna also just detect 3 errors and correct 1. So basically, you're completely right in that saying we could have chosen the middle 3 to flip, right? But that's kind of the case with imagining we had, let's say for the binary repetition code, we had like 10001. We're going to flip this, correct this to 00000. We're not really going to correct this to 11111. The reason why is because if you correct it 11111, we're going to assume 3 errors happened. And it's more likely, well, it's not more likely, but I think we just always assume less errors happen. So yeah, we can either say, in this case, we can say, we can either not correct it and just say an error occurred because we saw 2 errors or 3 errors, depending on which way you look at it, or we can correct and detect 2 errors. Does that make sense? Cool, awesome. Now, another question. So we have a binary linear code C with the parity check matrix H, and a code word that's transmitted through a noisy channel in which each bit is corrupted with equal and independent probability P. For A, we are asked to find the probability that all errors are correctly corrected when using the minimum distance decoding strat. So remember for the minimum distance decoding strat, basically we can correct well, the number of errors we correct plus detect must be less than d minus 1. That's what we know. So let's just first figure out how many errors we can actually correct using this matrix. So remember for this matrix, the distance of the code word that's basically extended by this matrix is equal to the minimum number of linearly dependent rows. In this case, d of c equals 4. Why? Because all 4 rows, if you take all 4 rows, then we have a linearly dependent situation. Because the first 3 columns, mixing up rows and columns, but the first 3 columns sum up to the last column. However, if you choose any 3 columns, they will not be linearly dependent. So no matter which 3 columns you choose, let's say first, second, third, they're not linearly dependent. First, third, fourth, again, they're not linearly dependent. So we know d of c here equals 4. So hopefully that will make sense. I think this is a theorem in the course notes as well, that d of c equals the minimum number of linearly dependent columns. So d of c equals 4 in this case. Which means we know e plus f is less than d minus 1. Which means we can correct 1 error and detect 2. The reason why we can't correct 2 is because if we correct 2, then we need e and f both to be 2. And 2 plus 2 is not less than 4. So we can either correct 1, so we can only correct 1 and detect 2. That's the best we can do. So A says find the probability that we will correct all errors successfully. And since we can only correct 1 error, it must mean that we have only 1 error happen in our transmission. To have only 1 error happen, it must mean that if you have 4 bits sent during transmission, for 1 error to be happen, that error can happen in each of the 4 places, right? So we have 4, ways to choose which bit is the error bit. For the error bit, that's probability p, and the 4 non-error bits, that's 1 minus p to the power of 3. So for there to be exactly 1 single error, it's 4 times p times 1 minus p to the power of 3. And that's how we get the answer for A, because we need exactly 1 error to happen in our code transmission. So hopefully that will make sense. If you have any questions, feel free to ask. For part B, we are given that, find the probability of detecting at least 1 error when using the pure error detection strategy. So it's a good thing we figured out what d minus 1 is, because now if you want to just detect errors, we know that we can detect 0 plus 3 is less than 3, right? So we can detect 3 errors. So to detect 3 errors, we're trying to find the probability of detecting at least 1 error, right? So we're trying to just find the probability that there is 1 error plus the probability there are 2 errors plus the probability there are 3 errors. Why? Because if there are 0 errors, then we can't detect it. Because the question says at least 1 error, right? And if there are 4 errors, we can't detect that as well. So we only want to detect these 3 cases. So the probability of detecting these 3 cases is just we add them up. And that's the same as just taking the complement, which is 1 minus p of 0 error and 4 errors, which is equal to 1 minus p to the power 4 minus 1 minus p to the power 4. And hopefully that should be the correct answer. Any questions? No? Okay, cool. And we'll see that in the first case, the smallest set of columns which are linearly dependent is 4. So the maximum error we can correct is 1 error. And to correct exactly 1 error has to happen, which will happen with the probability 4 times p times 1 minus p to the power of 3. Similarly for part B, we either add up these 3 or take the complement, and they will give the same thing. So hopefully that makes sense. And if you're wondering how we kind of get this term here, y p of 2 errors is equal to 6 times p squared times 1 minus p to the power of 2. We get that through the formula 4 choose 2 times p squared times 1 minus p to the power of 2, which is also the PMF for the binomial distribution, which you saw on slide 3, I think. So you can have a look at that if you're confused. But that's essentially how we got these 3 terms. Cool. Last thing, I think, before we take a break, are generator matrices. And essentially, generator matrices are just a way of representing the basis of all the code words. So essentially, let's say we had the code words 1001 and let's say 1100. So let's say these 2 are the basis for our code words. So we have the code words 0000, 1001, 1100, and 0101. So these 4 code words are extended by the basis vectors as shown above. So one way to represent this is with the generated matrix G, which is just given by 1001 and 1100. So you write the basis in a row like this. And that's one way of representing all the possible code words that we can come up with by coming up with the basis vectors and writing them in the row format like this. So that's generated matrices. And the reason why we want to care about generated matrices is if you first put H, which is a parity check matrix, which is basically what we've been working with so far, into standard form, because H can be anything, right? As we've seen before, for H for the 7-4 matrix was something like this, 100, 010, 110, and so on. If you put it into standard form, which is we first have an identity matrix up front, like this, followed by the rest later on. So we have the rest of the matrix later on, like 101, and 011, and 111. If you put H into this form, this is what we call the standard form. And we have a M by M identity matrix, followed by a M by K matrix next to it. And this is known as standard form parity check matrix. And if we find H dash, we will have a connection between H and G. And the connection we have is if H is in the format of the standard form, then we know G is also in the format of B transpose IK. So, as an example, let's take this H matrix, right? The corresponding generator matrix is given by, we just first take B transpose. So remember, this is B here. We take the transpose, which is simply just 1101, 1011, and 0111. And then we put the identity matrix after it. So we have 100, 010, 001. And basically, this is the generator for G.
Cool.
Sorry?
000.
Oh wait, sorry, yeah. Yeah. Good shot. Thank you. Yeah, awesome. So yeah, you'll notice that the identity matrix dimensions are different between the H and G matrix, and that's on purpose as well. So basically, this generator matrix will basically generate all the code words which are valid under this parity check matrix. So that's the connection between the two. If you put them in the standard form, we can get the other one for free, essentially. And there's a small catch, but this is meant to be a minus here. But the thing is, we ignore this minus in mod 2 space, because minus 1 is still equal to 1 mod 2. So basically, you can discard this minus in mod 2 space, but if you're working in mod 3 space, the minus will come into effect. So just be wary of that. And I think this is going to be the final question for now. Maybe there's one more. But we have a binary linear code C with a parity check matrix given below. And now we're asked to find a basis. So the question asks to find a basis, you should think of finding G. Why? Because G basically gives you the basis of the code as its rows. So we can try that now. So we have the identity matrix here, and we have B here. So we can simply say G equals B transpose with another identity matrix that is of size K. And B transpose here in this case is equal to 1, 1, 0, 0, 1, 1. And we have an identity matrix 1, 0, 0, 1 here. So now we know the basis is spanned by 1, 1, 0, 1, 0 and 0, 1, 1, 0, 1. So these two vectors are the basis vectors for our code C. So hopefully that makes sense. All we did was find G, and then we take the rows to be the basis, because the rows are the basis of the generator matrix. So yeah, hopefully that makes sense. And again, we have similar working out here to give the same basis as above, I think. Cool. Now we have, okay, last slide. We're now working, if you're working at higher radii, basically we have to be wary that the conversion between them, the negative sign now will be necessary. So if your H matrix looks like IM followed by B, then your generator matrix must be minus B transposed followed by IK. So the minus is very important for higher radii. And again, for high radii, you're allowed other numbers like 2, 3, and so on. And after calculating the syndrome, it is more difficult to now identify the linear combination to form the syndrome. But yeah, I'm sure you guys can do it in the exam as well. So yeah, I think that's it for the first two chapters. If no questions, I think. With the sign, for percentages minus. Oh, you might be right. Good shout. This should be a plus and plus. Thank you. Cool. If no other questions, I think we can take a break. What do you? Cool. We'll take a break for 5 minutes and then we can reconvene. And Brendan will go over chapter 3 with you guys. Cool. I think expected to be down.
That's
Good thing you have the room for 3 hours then, I guess.
usually these things go on. I think I can speed run this.
So just doing one thing chapter.
Just for today.
Oh.
Doing chapter 4 tomorrow. Then Matthew will do chapter 5 to 7.
Oh, okay, nice.
Still wait.
Hey, just don't. Wish I could do this again.
The stream's still working.
That's good, boss. That's good.
Like, give me the one in the first job.
Share the slides here.
They should be uploaded, yeah.
That's it. This is a new transfer.
Comes under. I didn't actually.
What, would it be all good if I get lunch halfway through?
Yeah, if you want to leave now, that's fine.
Oh, okay, cool. Stay put. We'll just get lunch on it. It's have breakfast. Lunch, yeah. Oh, I slept at like 5 last night.
Yeah?
Yeah, I went to bed at like 2, but I just couldn't sleep. Like, it's one of those days when like you're just not tired.
You're just like in bed, but
Yeah, and it kind of sucks because it's kind of humid and hot yesterday as well. So yeah.
yeah, the heat doesn't help.
So yeah, woke up really late today.
Yeah, fun. One. How do you rinse the random? Well, you make it. Oh.
All right, we'll reconvene now. So if you don't know me, I'm Brendan. I'll be taking, for today at least, this third chapter on compression coding, and tomorrow I'll be taking information theory, and then Matthew will take the last 3 chapters if you want to join us tomorrow, same place, same time, so also 12 to 2. As you can probably guess, we're a bit short on time today, so I'll go through some of the exercises a bit quickly, but I'll try to go through the main intuition of what we are looking at in this chapter, because that will probably be what's more important in your exam, given that you by now would have experience doing a lot of these questions, but just maybe need some recap on intuition, and that's maybe why you're here. Because that's something that Thomas might change within the exam questions. He might just put a little spin on it so that you can't just do what you've done for the test so far. I'm sure you're fine with the computations. Alright, so we'll get started. We'll dive straight into it. What we are looking at in compression coding essentially is if we are given source symbols and probabilities that those would be transmitted, what we want to do is encode those in an efficient way such that their codes effectively have the shortest length possible. We'll talk about the expected length later on. But we are going to be focusing on what we can do to, I guess, vary the lengths between our codes that we want to use to correspond to each of our sources, such that we can code efficiently. And we'll talk about how we can define efficiently and so forth. But the idea, similar to, you may be familiar with, say, Morse code, which has T, for instance, as I think 1 dot, and then a less common letter such as Z is a few dots and dashes. You want to encode the more frequent symbols with shorter code words so that when you're trying to look at your code being transmitted, you can interpret it efficiently, so you don't have to use as many characters when you have more frequent occurring sources is the idea, right? So the average we're trying to reduce. So we have 2 definitions here that will be important to us through important theorems such as Kraft-Macmillan throughout this topic. So the first one is uniquely decodable. So what uniquely decodable means for a set of code words is that we can decode it unambiguously. So as to say, there's no double ups in any combination of code words. We'll look at an example in a second of that. The second definition is an instantaneous code, sometimes referred to in computer science as a prefix code, or non-prefix code, one of the two. And that is where no code word is a prefix on another. Okay, we'll explore a little bit on the link between the two, but when we get up to Kraft-Macmillan, we'll figure out that for our purposes, they're essentially very similar. Right, so look at this example here. So we have the example of the comma code. So you can think of this code as a tree where you have, say, you're starting 0. This is your first C1. You have a 1 here. You get up to C2. Oh, if you go, sorry, you have to go up here. C2. You can continue your tree. This is C3. And this is C4. You would have seen Thomas drawing diagrams like this. So say to get code word C4, we follow this tree and go up. So 1, 1, 1, 0. And it turns out that this code is both uniquely decodable and instantaneous. So you can hopefully see by the way we've drawn this as a tree, then it's going to be instantaneous because no code is a prefix of another, because they all the codes lie on unique branches of the tree is a way to think about it. We'll talk about how that relationship between the tree in Graph Macmillan when you have that k value, if you remember that. And it's going to be uniquely decodable as well, because you can, I guess, you look at whenever you see a 1 occur, you look at how many times the 1 occurs. If it occurs once, then you're looking at C2. If it occurs twice, you're looking at C3, and 3 times C4. Okay, and so more important examples maybe of when we do not have either uniquely decodable or instantaneous codes. This example here would be a code that is uniquely decodable but not instantaneous. So we can see that if we look at S1 and S3, S1 is a prefix of S3, prefix if you remember, meaning that the start of S3 is exactly S1, it's 0. And so it is not going to be instantaneous, but you can work out, try and error a little bit, that it is, it's not uniquely decodable. So it's not instantaneous, and if you actually went through the logic, yeah, you can actually combine S3 together with S1, that would be equal to S1 and S2. And that's what they say, yeah. So that means that it's neither uniquely decodable. So yeah, you have to go through actual examples rather than just by looking at it. So in this case, it is not uniquely decodable. And so you would develop some trial and error in determining if it is uniquely decodable is really the only way to do it. For this example, is basically the comma code, but in the comma code here, but backwards essentially. And so from that, you can also use the same logic to say whenever we see 0 1s, then we're dealing with S1, the 0 to like initialize the start of a code word. And likewise here, if you have 1 1, you can say that's another code word with the start at the 1, at the 0, sorry. So you can think through different cases, but in this case, it would be that this code is uniquely decodable. However, similar to what we said before, S1 is a prefix of both S2 and S3, so it is not a prefix code, unfortunately. Okay. Right. So I guess another takeaway from this is that this comma code type code here is effectively very similar to the comma code we saw before. As in, if we just take S1 through to S3, these codes are effectively the same. And we notice that this one is instantaneous and uniquely decodable, whereas this one is just instantaneous. So that's going to suggest what we're going to look at with the Kraft-Macmillan theorem, which says that if there is a uniquely decodable code that exists, instantaneous code that exists, then it can also be uniquely decodable essentially as well through changing your jiggling around your your alphabet in each code. Yeah. Okay, so and you can also hopefully remember that if a code is going to be instantaneous, then it also has to be uniquely decodable. Because otherwise, the condition you need for it to be not uniquely decodable, you can think about is that you have to have a combination, 2 different combinations of code words that are equal to each other, and in that way you have to have the start of that be one code word as a prefix of another one. Like if you have a chain of say This is, say, C1, this is C2, so this is C3, let's say C4. So this is what it might look like when you have a combination that's saying, say C1, C3 is equal to C2, C4, not UD, then of course, in this case, if we're saying these two are equal, then C1 is a prefix, so prefix of C2, so it's not instantaneous. Okay, so uniquely decodable then implies instantaneous, but the converse is not necessarily true for a fixed code.
Instantaneous applies uniquely decodable.
Oh, sorry, yes, instantaneous applies uniquely decodable. That's right. Yeah, because we looked at the contrapositive. Thank you. Yes. Okay. Right. So in terms of actually working out what our source symbols that were sent were when we are given a code, so we want to decode, what we do is we break it up, because if we know it is uniquely decodable, then there's only one way to do it, so it's not ambiguous. So for this example, we can look through each section of our code. We stop once we get, or we start from the beginning, we stop once we get to the end of one of the different codes. So in this case, we'd go until we get to C2, so the 0, 0, so we have S2, and then we have 1, so that has to just be this one, because there's no other ones that start with 1. Then we have 0, 1, S1, S3, and you can continue on and so forth, which is done down here. So S2, S1, S3, and you can continue on as you're just breaking this up as you go to the different codes. You find which code corresponds, because there's only one, because it's not, because it is going to be uniquely decodable, and so that's how you proceed, given a uniquely decodable set of codes. Okay, and then this is the important theorem that I wanted to focus on. So the proof is given in the lectures. It's somewhat important because my understanding is the proofs are accessible to some degree in the exam. So what we're looking at here is if we are given lengths corresponding to our code words in increasing order, then we have three equivalent statements. So we call this summation, we call that K. So the K value is important. Having that K value, where R is our radix here, radix of our code, so the number of symbols we use in that alphabet to write down the code, we can, if this summation is going to be less than or equal to 1, then that is going to be equivalent to saying that there is a radix R uniquely decodable set of code words for these specific lengths, and also an instantaneous set of code words. So like the strong claim here is really that it's going to be instantaneous. So like you're seeing this, we might as well consider these two as the same thing when we're trying to find, we're saying we can find it such that it is not only uniquely decodable, but also instantaneous. Sorry, not only instantaneous, but not only uniquely decodable, but also instantaneous, because instantaneous is the one that we want a bit more. No, the other way.
Instantaneous is like stronger.
Yeah, instantaneous is the strong one. Yeah, so we want instantaneous.
Left and right.
Yeah. Did I say something wrong on the previous slide? Uniquely decodable implies instantaneous. Instantaneous implies uniquely decodable. Yeah, so it is this one. Yeah, so I implies instantaneous. Okay.
That's good.
Yeah. Okay. Yeah, so thinking through the logic helps you. What we're looking at then, let's go through maybe the intuition of what this K value is. So you can think of this K value in terms of that type of tree we spoke about. So we talked about that tree you can express the code words on. So in terms of a higher radix, that tree would look a bit larger. So you're trying to fit if we're trying to talk about a instantaneous code, you can look at the leaves of that tree be where you end off in your particular codes. For instance, we could say if we have code words 0, 2, 1, we go 0 and then 2, then 1 here for say C1, and then you have a 1 here, say 0, 0, say C2. Okay, so let's say this is ternary, where R is equal to 3. So what this is effectively saying, if this is less than or equal to 1, we're basically saying we can construct this I code such that it is always going to fit on this tree, which is what we effectively want. And we know that if we can put it on a tree, then we can make it instantaneous. That's how we effectively constructively in practice make our instantaneous code, given that k is less than or equal to 1. And the relationship between this type of tree we want to make, given these lengths, would be that if you look at each term of this sum, we have expressions that look like 1 over r to the l. And so since we have l is the length for that word, so l is saying we are going and branching l different times. So effectively saying that the r to the l is the probability, assuming each leaf of the tree is effectively equal. Like you're saying, the probability splits at every time into 1 over r different parts. So you can say that if the sum is less than or equal to 1, then you can fit that 1 probability that you're at most having at your advantage into your you can fit your code words into that effectively. Okay. So if we look at an example here, when we're given these code words, then computation can show that when you look at this k value, it is greater than 1, and so there is not going to be I should type it here. Yes, there is not, since there is no uniquely decodable code, or either no instantaneous code by the equivalence here, because this k value is greater than 1 in this case. When we are given now these lengths, we can compute similarly, if I have it here, that the k value is less than or equal to 1, specifically it's 25 over 27. You can look at computing that. For instance, you'd have k is equal to, in this case it's radix 3, 1 over 3 to the 1, plus 1 over 3 through these two, and then to set this, it's plus 1 over 3 squared, and you can continue on, so that's where the 9 comes from, and the 4 times 1 over 27 comes from having 4 length 3 code words if you want. And so the way we can constructively do this, we have it done there, is you can try to start making your tree from, say, the top, and every single branch you go from the top down effectively. So we can start here, we can go 0 for this first one, so that can be C1, then 1, because we also want length 1, so in 2, we have to go 2, because we're working in ternary, we have access to 0, 1, and 2 as our characters. But we want this one to be a length 2, so we can go up here, go 0, C3, 1, then we want length 3, so we can go 0 here, 1 here, C4, C5, say, and go 2 here for, say, we can actually fill this one up, C6, and then since we want the last one to also be a length 3, we can go C7 like so. This would be 0. So that would be similar to what's done here. Yeah, so we go, the first one is going to be 0, 1, 2, 0, 2, 1, 0, 2, 1, 1, 2, 1, 2, and then 2, 2, 0 is how we constructed this. And you can see in this example, there is still a bit of space on the tree in the sense that we could have branched here or here instead. Like this last code word could be 221 or 222, and it'd be the same in terms of still being instantaneous and uniquely decodable. And the reason why that is occurring is because in this case k is less than 1, so we haven't packed as much as we can in, where we can still construct the code like so. Okay, So we'll talk about later how we can try to, given like a fixed set of probabilities, how we can try to vary the length such we fill the tree most efficiently to make the goal being to make our average code word minimal. And looks like that's what we're trying to get here actually. So this is some motivation for the Huffman algorithm we're about to talk about. So what we are interested in is trying to get the average code word length, so the average number of characters we need to transmit given the same amount of sources to be as minimal as possible. So what we're looking at, we have two terms here, basically, two items that we care about. The average length, which we can define as the expected value of the length of each of the codes. So noting that we're bringing in the probability, so that we're saying that we want higher probability codes to be less in length, such as T in Morse code has like 1 dot. And then we can also define the variance in the typical statistical way as well, which is the expected value of the length squared minus the expected value of the length squared. Okay. So this is not typically used too much. It may show up, but it is just the variance in the same way that this is the expected value, average value you can do that as. And we say that if we are given the probabilities and we are allowed to choose our lengths to correspond to our different source symbols, then we say that a uniquely decodable code that can correspond to those source symbols is going to be minimal, which is what we want. We want the minimal average length if it has the minimal average length over all the different possibilities. So if you consider all the possibilities, there would be a finite amount, but many of them, you want them. And I believe we're about to see, we have a few more theorems and examples before we get to Huffman's algorithm. We'll walk through that. But first of all, just some numerical calculations. If we have decide to have length 3, length 1, length 2 with these probabilities, then we can compute that the average length is going to be 5/2. But if you consider the same probabilities, and you also consider another uniquely decodable set of code words, instead of these ones, then you can get a lower average. Okay. So in this example, what we're effectively doing is like knocking off this last character here, essentially, to play around with it. And just note, in general, we do assume that we are looking at our probabilities in decreasing order, or sorry, not increasing, because they could be the same. What we look at with, so what we're going to look at with this theorem is sort of leading on from this. So the first thing we're going to note is that when we are dealing with binary codes, or really actually any codes of any radix, what's going to happen if we have our minimal uniquely decodable code, what we would have is that the length of the largest two code words would be the same. So we can, like without loss of generality, you can say, look at L1 through to LK in increasing order, where K is the number of source symbols, the number of probabilities that we have. We can, without loss of generality, put them in increasing order. We can, by shuffling them around if need be. And what would happen is that we can have the last two have the same length, because otherwise we might as well chop off the length of one of them, because we can think about, again, this binary tree where, say, for whatever reason I had, or like I had here, I can just chop off this one and we still have a uniquely decodable code. Actually, I won't, what should I call that? Just reference that this is going to be for this example.
You also have K equals 1 in this.
You would have K equals 1 in that case, yes, for this example. So we're looking at, I'll make a little dash here. Yeah, have C7 equals 2, and K equals 1.
You're not saying 1.7, then you're adding the 9.
So that would make it K equals 1. Yeah. Yeah, and we can see that it packs the tree. There's little branches you can take. Excellent. So that's what we can do here. For, just say, so anyone that's reading the annotations, for And it turns out when we look at binary specifically, like the way that the splitting into twos works out nicely is that specifically k would be equal to 1 when you have your minimal uniquely decodable code. And if we choose it to be instantaneous, which we might as well, because we have that Kraft-Macmillan theorem that tells us if there exists a uniquely decodable, we can make it also instantaneous by shuffling a few different characters around. We might as well assume it's instantaneous, in which case the last two would be on the last branch. They differ by just one. They'd be like we saw kind of here. They differ just by this is the case of, it's not the binary case, but I think it holds true in general. They just differ by one, this one symbol here at the end. Okay, but then the prefix would be the same, but they would differ. Okay, and in binary it does work out nicely that you can get k to be equal to 1 by your choice of lengths and still have it be uniquely decodable. Okay. Okay, so we have this example here. We have code words and probabilities. And you can think about and I guess prove if you want to using Huffman's algorithm later on that this is going to be uniquely the minimal binary I code. We can see that it satisfies these properties. We can represent it in increasing order of length. We can have the last two code words only differ in the last position. Let's just see. In this case, q equals 3. These two only differ in the last position. And you can compute as well that the sum of these three is equal to 1. Half plus 2/4 is equal to 1. And so our k value is equal to 1 in that case, meaning it's pretty much as efficient as we can get, which is nice for us. Okay. So now we'll look at Huffman's algorithm. So as you can maybe tell, I'm a big fan of Huffman's algorithm. I think it's a quite nice algorithm. It's what you might describe as a greedy algorithm to find to compute the lengths that you want. And of course, it'll help you construct later on, corresponding to the minimal. It'll give you the lengths through actually explicitly a tree that we'll construct in a second that corresponds to the minimal uniquely decodable code given a sequence of probabilities. So if for some reason you want to read through the whole algorithmic steps, you can read that here. But like with Thomas, I'm pretty sure, better to go through an example. So just to note, in this course, unless it's changed this year, you want to be using what's called the place higher strategy, where we'll explore what that means in a second, but let's get started on this example. So what we do is we place our probabilities in decreasing order, 0, 1, and what we do is we combine the two lowest probabilities into one. So this would be 0.3, and we combine them together. We get 0.3. And in this case, we can talk about how we want to use the place high strategy. You can put 0.3 up top, below this 0.3, 0.3 down here, go like this. I don't think I want to really put arrows, maybe let's do it like this here. And we just drag everything else along. So we keep, if you think about this as like a list, we keep the list sorted or the array sorted if you have a computer science background. And then we keep going. We combine the 0.3 and 0.3 to get a 0.6. And this here, 0.3. And put the 0.4 below it. And we can combine these to get 1. As so. Okay. So then we can construct our tree from this. The tree would look like a 1 at the top, and then we can put let's put the 0.6 here, and the 0.3, 0.3, 0.2, 0.1, and so we could put 0, 0, 1, 0, 1. Believe is the conventional way of doing it. Correct me if I'm wrong. Like this. Okay, so, and there'll be 1 here. So our code words, this looks consistent with what was done here, that's good. Our code words then reading off would be, C1 would be, this 1 here, then 0, 1, then 0, 0, 0, then 0, 0, 0, 1, as they have done here. Excellent. Any questions? Is this inconsistent with anything you've learned in class in terms of the just like subtle strategies? I'm pretty sure that you still use the place high strategy in general, and the way I've constructed the tree is consistent as well, just to make sure. Okay, that's good. Okay, and then in terms of actually, once we have this, we can just plug in the numbers so we have the different lengths of our different codes. But if we want to be, I guess, a bit more efficient sometimes, we can use what's called Knuth's. I think it's usually called lemma, but maybe it's just, lemma's theorem anyway. Knuth's theorem is useful because it allows us a more efficient way sometimes to compute the average code word length given our Huffman code, because it's going to be the sum of all the child node probabilities. I should say, right? If I remember correctly, it was the parent node. So if we look at our previous example, it's telling us here that we have the average code word length would be 0.3 plus 0.6 plus 1. So we can get the 0.3, 0.6 plus 1. Okay, so should say parent node probabilities, which is what I'm more familiar with. I don't know what it says then. Parent. Okay, my bad. Don't know how I missed that, but I always understood it as parent, so I must have just assumed that was correct. So it's all the parent node probabilities. The proof of that is, I guess, a bit technical, but just like it works out, I guess. You can think about it like the parent node, since it comes from adding all the children, you get those, think about the length would be sum of all the lengths times the probabilities, so that you can split that up into like what this effectively becomes is the sum of all the probabilities times the sum over Li times P. You can think of it like that, like summing Pi Li times, and that's effectively what comes up here in a similar way. But you can just take the word for the theorem. In this case, it would be L would be the sum of these. L is equal to 1.9. And if you're interested in why I call this a greedy strategy, that's kind of how it is, because like inductively, if you imagine the process going, you add these up together and well, first of all, like if you ignore these, you have a sub-problem with still probabilities, and then you can combine the smallest ones together again with like the smallest sum, which is what you want. That makes any sense. Okay, so we talked about that for the binary case of Huffman's algorithm. To generalize to the case of radix R, what we want effectively to be efficient is, in the case where we talked about combining the smallest two, in the binary case, we combine the smallest two probabilities together. So we had P1, P2, P3. We combine these two together, and let's say it places it there. Then we combine, say, P1, P2, let's say P2 dash. We combine these together, say. That worked out perfectly fine in the case where our radix was 2. But the problem that might come up when we have a radix of, say, 3, when we try to combine together. First of all, when we're dealing with radix 3, we want to combine more than 2 at once, because we have 3 different branches that are possible, say when R is equal to 3, for instance. So if we just try to do it naively when we combine the 3 lowest, which might seem like a generalization to a radix 3, we could say this P2 dash P1, for instance. Then the problem is that we're not really using this possible third branch that could be here. And we want to, I guess, exhaust as many branches as possible, like intuitively at the highest level of the tree as possible, because that would minimize our average code word length. So we don't want this. We don't want an example like this. So what we have to do instead is add dummy symbols to our code words of probability 0 at the bottom effectively, and then apply our algorithm. So effectively modifying the input. In this case, we want to do it such that we have n equals to 4, r equals to 1. The formula that we use is we want to add a number of code words such that our total amount is equal to 1 mod r minus 1. So we want n plus, let's say a for the number we add, to be congruent to 0 mod, 1 mod r minus 1. This one. So that would be saying that 4 plus a is congruent to 1 mod 2. So a would just be 1 because 4 is already congruent to 0 mod 2. 1. So we would be adding this new symbol, P5 is equal to 0. Which is again 1 equals to 0. And then if we apply our algorithm, it works out nicely such that we can combine these two to make, say, P3 dash. This could be copied over, for instance. And then we could get to combine these nicely on the top layer. So we get to use as high as possible, as many branches in our tree as possible. Right, so that is what we use there. And what we have here. So we have an example of doing that, where well, I basically walk through an example. Another example here we have r is equal to 3, we have 6, so we want 6 plus the number we add to be congruent to 1 mod 2. So that should be 1 again, I believe, as well. Yeah, 1. Yeah, we add 1, simple, yes. Okay. So you can do it like this. You have a dummy 0 probability, which just means that when we sum these together, it gives us 2. And we can see we're at the top of the tree, we're using all 3 branches here. And then we aren't using this branch because this is isn't an actual probability, but we are using these two because we can't really fit anymore. In this case, k, in terms of ignoring this one, k wouldn't be less than 1 because we spoke about earlier, it is true in the binary case that we can make k exactly equal to 1, but not necessarily always in the radix r case. Yes?
I think I came up with a way to think about the algorithms. Each step reduces the number of elements by r minus 1.
Yes.
So you want the last layer to have 1 element. So if you're repeatedly subtracting by r minus 1, it sounds like taking 1 element.
You want r of them in your last layer, and you're subtracting in your previous steps r minus 1. It's because you're combining r of them into 1. That's how I understand it. Yes. I believe that's what it's explaining here. That's what, apologies, I tried to explain here. Yeah. At every step of your algorithm, you're combining r symbols into 1. So you delete r minus 1 every time, and at your last step, you want to use all of the different branches. You have 2 availability, so you want the sum of k times r minus 1 plus r to be congruent, to be equal to your n. So if you rearrange that, you want mod r minus 1, you want n to be congruent to y. Okay. Thank you. All right. So that should be all. Yeah, you can in your turn verify that is the correct use of the Huffman algorithm. It's just really the same as what we looked at in the binary case, but generalized with our additional dummy symbols and combining 3 instead of 2 at a time, because now we're dealing with radix 3 instead of 2. And likewise, if you're doing radix, say 4, you're combining 4 of them at the same time. Okay. Right. So another way that we can try to compress codes is, instead of considering every single source symbol individually, we consider combinations of the two. So I think this gives too much insight here. We could say if we have S is equal to, say, AB, I believe this is a common type of example Thomas gives, then we could consider S squared would be occurrences of, say, A, and then AB, and then BA, and then AA. And these would all have an associated probability of occurring, given the probabilities of A and B occurring. So BBs. And I believe for now we assume that we have independence on the next symbol occurring based on the previous. We will look at the case where that's not going to be true when we go to Markov chains, but for now we assume independence on the next symbol that we get, or rough independence. Like it's an assumption, may not necessarily be true, but just for simple mathematics we let that happen. So yeah, we denote Sn as a Cartesian product of our source symbols. So we're combining, it would be like a vector you could think of size n. So in this case, it's a vector of size 2. We have our first element could be A, second element could be B. So that's, say, this one, or other cases. And say the probability, if this has P1 probability, this has P2, then this would have probability as probability, P1 squared, and you can work out the rest for the otherwise. So what we are trying to get at here is that if we effectively try to do this for some values of n, we can try to then apply a Huffman's algorithm on this new set of sources we can think of from our odd set of sources by combining those together and the different combinations that can occur up to a specific length that we call n. And then what can happen is that we might get a shorter average code word length. But of course, we are doing a bit more work here in like the processing in terms of we have much more code words than we need to have now, but we can still get the average code word length to be smaller in general. Okay. All right. So yeah, like I just drew out, we have this example of A and B with these probabilities 0.7, 0.3. We can make S squared with these probabilities. So this one comes from 0.7 squared. And these are, like, for convenience, they're sorted in non-increasing order, as we wanted before. So as I said, given these new probabilities, what we could do is run Huffman's algorithm on this new set of probabilities. We would get this, or something that's equivalent to that. The average code word length is then 1.81. You can verify if you want. Okay. And I would say, that is per symbol in S squared. So in terms of our original sources, you can think of per like character we're trying to transmit, we can divide by 2 to get it to be 0.905. Right? Whereas if we just try to, if you try to apply Huffman's algorithm on this case, you can only just combine together. So your average code word length would be 1 in any case, because the only way to do this would be with, the best way to do this with, the minimal UG code is, I guess without loss of generality, let's say C1 is equal to 0, C2 is equal to 1, L is equal to 1, and this is better than that. Okay. So you may expect, and I believe this comes up in not until we look at information theory tomorrow precisely, but it will come up that the more times we do this, the better the average code word length gets, which is quite intuitive, I would say. So now we are looking at the case where we don't assume independence on what the next character source symbol that we are meant to see based on the previous one. And so we have, I guess you could think of it, Markov chains are meant to represent transitions between different states. So our states would be what our current source symbol that we get is, and what the next one would be in terms of our message being sent. So specifically, we can define our, we represent that as a transition matrix, where the probability in the ith column shows the probabilities of each source symbol occurring after getting the SIth source symbol. Okay. So that's all we really need. We are also given this what's technically called an eigen vector, which says that in the long run, that's what the probability of getting a specific source symbol would be. So there's a bit of interesting linear algebra related to that eigenvector. If you're interested, I believe Thomas has recommended some resources on that, or maybe keep it in the slides a little bit. But we won't worry about that too much because, to my understanding, the eigenvector is always going to be given in these questions, but just understand it as the long run probability of the source symbol occurring, not just like the what's it called, the conditional probabilities that we are given in the matrix. So for instance here, we talk about how in the ith column it's the probabilities occurring after SI. So for instance here, 0.4 is saying we're having a 0.4% chance of getting S1 after we have gotten S2, for instance. Okay. And in the long run, our probability of getting S1 at any given time would be 56 over 145. So that's saying that since this S1 is 56 and S2 is 53, we're a little bit more likely to get S1 more times than S2 in the long run average. Okay. Yeah, I believe that's just what it's saying here. Oh yeah, so I'm just explaining basically what this is going through as well. Right, so there are two different ways we can do then Markov encoding for these type of dependencies, where we have conditional probabilities. The first way we can do is just the kind of the naive way, where we look at the Huffman code where we just apply the equilibrium, this eigenvector probabilities, which say give us the long run average, because that's maybe what we can try to do. And then alternatively, we can look at the conditional Huffman codes, where say half I is going to be the ith based on the ith column of the matrix. So we would say we apply that half I, for the ith source symbol, such that we apply that code once we know the previous source symbol that was sent was a CI. Okay. And we can also define then the expected value of the length when we apply this second strategy to be the expected value of all the different average lengths of those codes, weighted by the probabilities of that source symbol occur. Okay. So go through precisely what we should do there. I'll play through an example in a second. Yeah, this example here, which is pretty nice. So what we say is, for instance, so in the at the starting off, we do have to encode using the equilibrium Huffman code, because there's nothing else to do at the start. But since we're talking about the long run average, we're talking about what we do after that, which is more important. So when we have a message like this, we encode S3 using the equilibrium Huffman code. And then what we do, since we know our previous source symbol is S3, we encode the next source symbol, which is S1, using Huffman 3. So we get the code word corresponding to the Huffman 3 code for S1, and then we can continue on that. We do the same thing here. We use the Huffman 1 code to encode then S1 again, and then finally we use again the Huffman 1 code to encode S2. So hopefully this is more clear by this example here now. So we have a more concrete example of our matrix and our equilibrium. So if we were to apply Huffman's algorithm, I believe I have it here. So I'm sure you're capable of doing so. We have the results over here. What we are going to do is encode and decode a message, which should be sufficient to see, to, I guess, remind ourselves what this is doing. So we want to, first of all, we can compute the average code length for our Markov, what we say is for the Markov encoding, compared to the equilibrium encoding, which would be the weighted averages of each of the average code word lengths for the different Huffman encodings, which would be 1.47, just a little computation. Now what we're interested in is encoding S2, S1, and S3. Okay, so what we start off with, as we said before, we say that we encode starting with the equilibrium codes. So we get 0, 0 to start off with, so this is equal to 0, 0. Then since we had S2 previously, we go to Huffman 2. So the Huffman codes we use when we know the previous code was S2, and we get our S1, so that would be 1. Then we go to, since we know the previous one was also S1, we go to Huff1, and we want to get S1 as well, so we go to this 0, because we know the previous code was a 0. Then finally we go to we try to get out S3 from also Huffman Huff1, which would be 1, 1. So hopefully you can see how this generalizes, and this should be here. Next step we want to do is then have a look at an example of how we are going to decode. I believe we'll probably down here. We have the same codes probably down here. We want to decode this message now. So the way we do that is we said we wanted to start off using the equilibrium Huffman code. We start off using what we find where the first code word stops. It would be the 0, 1. So the 0, 1 here. So we know we have C3 starting off. Then we have to go to C3 because we know the previous code word was C3. So we have to use the conditional Huffman encoding for that in the next code word, which would be 1, 1. The next place we have to go to, so C3 again, actually, so we go back to Huffman 3. We can see the next one would be then C2. So now we know the previous one was C2, so the next symbol we have to encode will be based off that. And then we have 1, 0, or we can only use the 1, so we use C1, and we make it all our way to different color, Huffman 1, and we encode this final 0 here. So this is decoding it to 33211, which should be correct. Yeah, there we go. Any questions on this? So hopefully that should remind you how this all works. All right, so the final two things we'll look at, so if we're going a bit over time, would be just two little cute algorithms on how we can try alternative methods of using efficient encoding and decoding to be trying to compress our codes. The first one is what we call arithmetic encoding, that uses a little bit of the arithmetic of real numbers splitting into smaller intervals to encode our message, and also kind of doing the reverse to decode. Specifically here we need a little additional source symbol called the stop symbol to tell us where our message stops. In order to we navigate through the real line basically, and we find once we get up into a interval that's belonging to, say, the stop symbol, then we know to stop. In terms of decoding, we'll see this in action though. So we will look at this example here. So what we want to do is encode with the probability 0.2, 0.4, 0.1, 0.3. So the way that I always think about this is we put the cumulative probabilities on the real line. So we have 0.2 here, 0.4 here, 0.6, and then 0.7, and then 1. Each of these corresponding, we jump up by the appropriate step. So this would be for A's region, this would be B's region, this would be C's region, and this is the stop C symbols region. Okay, so let's look at the first example where we want to encode CAB. So what we do is, since our first one is a C, we go to this region. So we go into this region here. So we want to go between 0.6 and 0.7, which has length. And when you actually do this, it's better to do so with a table. So what we can do is, say, I think we keep track of the start and our length. So our start here would be 0.6, our length would be 0.1, and then we look at this length, and then our second symbol would be an A. So we want to go, A would be the whole length. So our start would also be 0.6, but then our length would be 0.1 times 0.2, if I'm not mistaken, because we're only looking at this sub-interval of this little sub-interval. So we're basically going into here now is what this is. Then we look at B. So we go, our start would be 0.6 plus 0.2 times its previous length. Put it there. 0.2, and our new length would be 0.4 times the previous one. So 2 times 0.4. And finally, we stop. So we stop by going plusing 0.7 times the previous length, which will give us our range based on the new length. So we'll see that actually the actual computations of what we just did. So it was correct up until now, and just skip the final steps. So the final steps would be our previous length was 0.8. We wanted to put that final stop symbol in, so our start then became going along 0.7 of that real line for the remaining interval that we had. So because we had this prefix 0.7 for our stop symbol. So we go along 0.7 of the way, and we go up to the width. In this case, the width will be multiplying by that 0.3, which is the width of this little region here. Okay. All right. So that's how we encode. And in terms of decoding, we want to decode, say, 0.8. It's a very similar idea. So to decode 0.8, like the first thing you can think to do is, since 0.8 first of all falls into this region, we know the first character is a, for instance, and then we break it up even further and further. We go looking into the 0.2 and continue on as we did previously. So it's really just the inverse of what we did. So like this, we work out what interval we're left with and its width the whole time, and then we find out, there's a little bit of algebraic here, but if you go through some examples, you'll see it in action. So for instance, when we're trying to look at 0.8, we find out it's first of all in the interval 0 to 0.2. Okay, so the remaining like stretched out scaled length would be that the rest of our code is within is at like position 0.4 of the number line, which corresponds to the B, if we remember. 0.4 was here. So we go to 0.4, which corresponds to a B, and then we say that that interval is of length 0.2 to 0.6. So we stretch it out by that scale factor, 0.4. So our remaining number, the distance we are throughout that interval, we are if we look at it, we're between 0.2 and 0.6. We want to find how far in terms of a scale from 0 to 1 we are through there, which would be, in this case, 0.4 is halfway, so 0.5 should be consistent with that, as you can see. And in that case, we again fall into the B region. We can see it's really the same thing. And then, say 0.5 is 3/4 of the way between 0.2 and 0.6, so we're left at like that 75% of the way throughout the real line, and we see that that lands us in the stop symbol region. Okay, so that means that we stop there, and then our decoded message will be A, B, B, stop. Okay, so hopefully you see the vision there. The final method, again, we'll just walk through. Example of encoding and decoding is for the LZ78 method, where we use a dictionary to encode and decode, so we keep track of what we have encoded so far, and use that in terms of extending it to encode the next messages. So we again want to use a table for this. So to encode this, we use a enumerated dictionary. So we have numbers for each of the different sources. So we would say the 0th one is just the empty one. Because then when we extend it, say for the first time, our first one would be, it goes, I believe the notation, just to make sure there's a top of two things. Yeah, you use, 0 then A. So we're saying this first thing that we're encoding is this A. So we're trying to extend what was one of the previous elements in our dictionary by one character. And we can't extend anything in our dictionary to start off with because we only have this empty character and empty word. So we can only extend the empty word by A to make our first one. Then for our second one, we want to say we can only extend this next part, B, by also the empty. But then what we can do, we can say this is A and this is a B. Since we already have a B, when we look at this one, we can say we extend this one, the second one, this B symbol by an A. So we are left with this one being AB. I just want to check this is consistent with what I should be doing so far. Yep, so that should be good. And then we have a AC. So we get this 4. We can extend the A symbol by 1. So we go 1, C. We're left with AC. And we can continue going to get this dictionary that we're going to set up. Okay. And so once we have the dictionary set up, then we just basically we plug in and send through our message, which is going to be this column of the table here. So you can see how we can continue this practice like so. We can continue to expand our dictionary, and we're going to output this column. Okay, so I did the table slightly differently, but you can see, I guess I should have the phi over here, would make more sense, wouldn't it? But we output that column over here. And yeah, we are left with the encoding here, which does look a bit long, but you can hopefully see that if we have a longer message than it does, you can't really make it precise enough for this course, but it does in some ways make it compressed. Okay, so the reason why we encode like this might not be too clear until we look at an example of decoding now. So let's look at an example. The final example for today would be decoding a specific message. So we effectively build a dictionary as we go and then try to use that to decode the message. So like the reason why we're doing all this in terms of this being our encoding, it gives the all the information required to reconstruct the dictionary, and as you go you look at what elements you're given. So let's try that. I believe this is usually the more fun side of using this algorithm. So we start off we start off with the 0 again, which is going to be the empty. And we're saying we're extending that by B now. We have B, so this would be 0B. I guess we can just like copy each of these into different columns. We have B, and then so B1, and we have A. So this would be 2. Oh, we can also have C, 0, 0A, 0B. Actually, we don't really need that column. Then we're using the second one, so this would be A extended by B. So this would be 4. 5 would then be 1 extended by C, so BC, a bit out of space. And then 5 extended by B, BCB. 6, 4 extended by C, which would be A, B, C. And then 6 extended by A, so that'll be B, C, B, A. And this does get quite long, but what would be B, A, C, A, B, B, C, B, C, B, just by, again, taking that column that we want. A, B, C, B, C, B, A. And I guess I don't have too much time to check that's actually correct, but it does look quite correct to me, at least here. So hopefully I haven't messed that up in any real significant way. So that looks fine to me. Does anyone have any questions? Okay. Right, so we will leave it there. Sorry for going a bit over time, but hopefully you found some value from that. Let me know if you have any follow-ups. We will try to, I think the best way to get these uploaded, probably just to have Thomas put them on your Piazza forum, so we'll try to get that done. Otherwise, join us if you're free and want to join us next tomorrow, from also 12 to 2 in the same room here. I will be presenting the information theory topic, and then you'll have Matthew, who is also a lovely presenter, presenting the last 3 topics. Okay. We will end the stream now.